I know not many of you have had a chance to get through some or all of the practice tests, so that is okay. So I'm going to go over some common mistakes and some highlight questions that I think are relevant. Worth noting, Paul is selecting the questions for this exam, but we have pretty much the same spidey senses, so if I'm reviewing it here, I think it's a very important question. So some common mistakes. The first thing is that I'm going to try to avoid putting this on the exam, but I accidentally put it on an in-class problem. If I write that the area of something is 1 centimeter squared, the area is not 0.01 meters squared. It's 0.0001, right? Each centimeter needs to be converted to a meter. So you need to multiply by 1 over 100 twice, once for each factor of centimeters. Again, I will try to avoid this because it confuses even me sometimes, or I just forget about it, but just do remember this. Next thing, just pay attention if a question talks about the diameter or the radius of a circular plate or a wire. Again, it's not like intentionally there to trick you, but sometimes questions use either, so I would just, before you submit the exam, just go through and check each question, just make sure you didn't make that mistake. Another very common one, and this is a particularly insidious one because you'll have no idea where you went wrong, is that remember that when you're doing like equivalent circuits for resistors or capacitors, you have 1 over Req equals 1 over R1 plus 1 over R2 for resistors in parallel or for capacitors in series. People forget to do this 1 over all the time, and I've started a bunch of times, but you're still going to forget because it's just too easy to forget. So if you're having trouble on a circuit problem, just make sure that you're doing this. Another thing that, again, is particularly insidious because you don't know that you make the mistake and it's hard to identify is the formulas for equivalent resistors and capacitors. They get flip-flopped, right? When you have resistors in series, you just add the resistors. But for capacitors in series, you have to do 1 over C plus 1 over C, and then do 1 over the answer. So just make sure to keep mentally straight that there are 2 different formulas depending on if they're capacitors or resistors in a circuit. Okay, I'll let you guys write that down. Some calculator stuff before I talk about the middle 2, which are like actually conceptual ones. Just make sure your angles are in degrees. Make sure your calculators are in degrees. I don't make you reset your calculators before the exam, but some people sometimes end up in radians for various reasons, so just double check that. And then also make sure, as in last exam, that when you are dividing by 25 pi, group the pi in parentheses or the times 10 to the 6th in parentheses. Otherwise, it's going to be a multiplication. Okay, now the 2 things in the middle, these are things that I did not lecture on to you. These are things that Paul taught you, so I just want to review really quickly. I've gotten questions about these, and I myself had a lot of questions about these 2 formulas, the Biot-Savart law versus the Lorentz force law. And I'm well aware that they are confusing topics and can be confused with each other even. So QV cross B, F equals QV cross B. I want to go over what this formula is for and then compare it to what the Biot-Savart law is for. So F equals QV cross B tells you how a charged particle responds to a pre-existing magnetic field. It doesn't tell you anything about if the charge is creating a magnetic field. It just tells you if there's a pre-existing magnetic field chilling somewhere, and I ask you, what is the force on a particle as it zooms through this field? That's what this formula is for. Okay, it talks about the force in response to a pre-existing magnetic field. Force in response to a pre-existing magnetic field. Sorry for the small writing, I didn't leave myself enough space. Okay. Oh, that's a B arrow, B vector. Okay, in contrast, The Biot-Savart law, which is the ugly one with mu naught, and again, it has those two forms, either QV cross R or IDL cross R hat. Okay, the Biot-Savart law, this tells you what magnetic field a charge creates, right? Moving charges create a magnetic field. They do feel them if there's another magnetic field that they happen to be in, but they also create their own magnetic field. And this formula tells you exactly how big and what direction the magnetic field is at each location. Okay, so this is what B field does a charge create? Okay, it tells you nothing about what force it experiences if it's in a B field. It only tells you what field it creates. And again, this isn't really a common mistake. It's just a very common, difficult topic. Perhaps a helpful analogy for some of you might be this formula on the right. It's very similar to Coulomb's law, E equals kq over r squared. Okay, it talks about the electric field a charge creates just due to existing. And the Lorentz force law is more similar to F equals QE, when you put a charged particle inside of some random electric field and you want to know the force on it. Okay, everyone good with writing that? All right. And then the last one before I go over some specific problems, I just want to remind you that, and this is a common mistake, when you have a negative particle, a negative charged particle, either feeling a magnetic field, so you're trying to find the force on it, or creating a magnetic field, the direction of the magnetic field or the force, depending on which question you're being asked, it's opposite what you get out from the right-hand rule. The reason is that, let's use the Lorentz force law as an example. This equation says that the force arrow, it's not in the direction of the V cross B arrow for all values of Q. When Q is a positive number, F is in the same direction as whatever you get out from doing V cross B. When Q is negative, the instruction is compute the arrow that V cross B spits out using the right-hand rule, and then flip it to get the F arrow. Right? You take a negative sign in front of a vector, you flip the vector, all of its components. And exactly the same for the Biot-Savart law. You compute V cross R hat, and you'll get a direction out, but if Q is negative, the instruction is you should multiply V cross R, whatever you got out, by a negative number to get the B field that it creates. Okay. Again, this is a common mistake if you're dealing with a negative charge, to forget that you need to flip. Yes? Yes. So I was just saying the analog of what was going on for the Lorentz force law with you need to flip it because F is not just V cross B. It's V cross B, but you have to multiply it by Q. Same thing here. B is not just V cross R. It's V cross R hat, but then you also have to multiply it by Q. So you might need to flip the answer you get from V cross R hat to get the direction of the B arrow. Okay. Again, this vector language can be tough for people, so feel free to come to me and have like a one-on-one talk, and we can get through it pretty fast. Okay, so I'm going to go over specific questions. If there's any questions on this, you can feel free to ask me throughout the review. Maybe my keyboard's dead. Maybe that's it. Okay, so the first question is one that I think we sort of did the other day. And these are all taken directly from the exam review. So if you have done it, maybe you have these as questions. If you haven't done it, when you encounter them again, you'll remember how to do it, so it'll definitely be good for you. So this was number 4 on the exam review. The question is, what current direction creates a given magnetic field? Okay, so you're talking about things creating magnetic fields, not particles or charges feeling forces due to magnetic field. So this question is going to have to do with the Biot-Savart law, right? Because it's about creating magnetic fields. What direction B field does something create? Okay, and again, the relevant parts of the Biot-Savart law for a current is this. Again, you could have numerical factors you will have numerical factors in front when you care about the exact size, but if all you're asked about is the direction of current that creates a certain direction B field, all you need is the vector parts. If it were a point charge, you would want to keep QV cross R hat from the Biot-Savart law. Okay. It's not QV cross B, it's the Biot-Savart law, it's QV cross R hat. QV cross B is if you're asked about force on things. Okay. Now, the Biot-Savart law is really good if I know I beforehand and I'm asked about B, right? All I do is the right-hand rule on I and R, and I get an answer for B out. Here, we're going to have to go and guess and check what direction of I gives us a specific B. Right? The Biot-Savart law sort of only works in one direction. Okay, so we're going to guess if I going out of the page in this wire works, and then if we're wrong, it might be into the page. And C and D are kind of stupid. They don't even make sense. It's a wire going out of the page. How can the current be clockwise? So let's just randomly guess it goes out of the page, and let's see what happens. So in that case, I'll do it in red here. In that case, I'm going to inspect some random point. I'm going to pick a point like down here. Okay, so R hat will go from the source to the observation point. And I'm going to do I crossed with R hat. And I get, to you guys, it's to the right, which is the right direction B field is created by that current. So that, you've guessed and checked correctly. It happened to be out of the page. Or sorry, the correct current direction that recreates this magnetic field is out of the page. Let's see what happens if you guessed wrong and you guessed B into the page first. In that case, I is into the page, and let's check what B field it creates at that point down there. R goes down, so the B field that that current direction would create would be left at that dot, which is not what I want. Okay, so you know that your guess was the wrong direction, and you should flip your guess to get the correct answer. Questions on this? I know this is a very difficult thing to pick up for the first time. Even if we've done it a lot, like, it is a very difficult thing, and it's fair that many of you still might be confused about it. Okay. Again, feel free to come up to me after class if you want to talk about this more. It can be very difficult. I'm going to... Actually, no, I can do this one now. Okay, this question is about induction, which is something that you and Paul went over very briefly, and I reviewed quickly on Wednesday. So this is going to be another question where you have to guess and check a current direction and see if it produces the correct magnetic field. So the problem is the magnetic field is out of the page, and it's getting bigger. It's getting more out of the page. So the circuit does not like that, and it's going to create its own magnetic field that needs to go into the page to oppose that more out of the page magnetic field. Okay, so we need to get a current that produces an into the page magnetic field. So we need to, oops, I'll do it in black. Need to guess and check a current through the wire that recreates a B going into the page. at any observation point inside of the circuit. Okay. So now take a couple seconds. Again, for some of you it will be easy, but for some of you it may still be hard. Figure out if I should make if I should make the current go this way or the other way. So use this as your initial guess. Have I go to the left, and see if it gives you B into the page at that dot or not. Go ahead. Talk with each other because your neighbor may be confused and you may get it. So.
Will be in the direction of like the.
So that's equivalent. So the.
Right, but like what law is that?
All right. Everyone good on this one? So if you do the right-hand rule here, this current I cross R creates a B that's out of the page. This is not what you need. So your guess was wrong, and instead of counterclockwise, the answer should be clockwise. And again, the reason you need B to be into the page is this is a question about changing magnetic flux, Lenz's law. B is getting more and more out of the page. The circuit doesn't like that it's getting more out of the page, so it's going to create something into the page. Okay, those are the two hardest questions. Now we'll be able to go a bit faster. Okay, this is called a velocity selector. Okay, there's an electric field that will push particles or positive particles down. Figure out what direction magnetic field allows particles to pass through undeflected. Now, a quick remark is that it doesn't matter if the test particles are positive or negative. It doesn't matter positive or negative. Because the response, if you are looking for the E field and the B field forces to totally cancel, for negative particles, both forces will flip direction. Like it will feel a force in the opposite direction of the E field and opposite of the right-hand rule from the B field. So it doesn't matter if you consider a positive charge or a negative charge. Let's do a positive charge. Okay, so what direction will a positive charge feel a force due to those electric charges? Obviously, it will be down. The electric force is going to be down. So we need a magnetic field that causes these particles moving to the right to feel a force upwards. So our question boils down to guess and check magnetic field that causes an upwards force. To cancel that electric force. Okay, the velocity of the particle goes this way. The question is, what B will create a force upwards? It might be into the page, and you're going to have to guess and check, right? Because the Lorentz force law is really good if you know V and B and want F. But if you know F and you need B, you need to guess and check your way. So everyone go and guess and check what direction B will cause an upwards force. You'll have to guess and check all four probably. This is a really, really good question, by the way. This was on my electrodynamics final, like a relativity version of this question. That's like a 6th-year electricity course. This stuff never goes away. All right, how's everybody feeling on this question? Again, this is a really good one. Even though I'm not making the exam, I can pretty much guarantee this is on it. Okay, so we need to guess the B field direction that causes an upwards force. If I guess that B goes down, then I'm doing V cross B gives me an into the page force, which is not what I need. I need an upwards force. If I guess that B goes out of the page, V cross B gives me a downwards force, which is not what I need. If I guess that B goes into the page and I compute the force, it would be V cross B. I'm guessing that B goes into the page. And I get that the force would be up. So into the page B field would be the correct answer. Again, feel free to come up to me after class. This can be very confusing for people, even if you've done it a couple times. Okay, something I want to point out that I don't think Paul pointed out, there are formulas for B fields near common objects. They are in the equation sheet. Okay, there's 3 of them. I'm going to need to pull up the equation sheet, actually. Okay, I just want to show you where they are, since they're kind of in a weird spot. Okay, they're under their own section in an image called B fields near common objects. Okay, there's the B field created by a line, a single ring of current that they confusingly allow it to be a ring that goes around multiple times, and then they have a cylindrical solenoid. These are 3 completely different objects. Okay? Magnetic field due to a wire, it looks just like the electric field due to a wire. Due to a current loop, again, a loop would just be a single ring, and maybe they allow the wire to go around a couple times so it multiplies the B field. That's what capital N is in that ring. But again, a ring is not the same thing as a solenoid, which has a bunch of rings wrapped around and around and around in a cylinder. Okay? The equations look very, very similar, but they're 3 different objects, and you need to be very careful not to flip-flop an equation. Yes? Oh, okay, so little n in a solenoid, I think I say it in the, I give this to you on the exam too, in the caption. Capital N is the number of times the wire wraps around the solenoid. People call it the number of turns. And L is the physical length in meters of the cylinder of the solenoid. little n is just the amount of turns divided by the length. It's the number of turns per meter. Okay, and again, this is in the caption on the equation sheet if you need it. Okay, and again, these equations, we had B due to a point charge or a small bit of current, but for extended objects, these formulas give you the B field near the object. Yes?
For the current loop, if there's like multiple loops, right, the radius will increase, so is the R greater to the max radius?
Oh, no. Okay, so his question was, as you add more loops to the single current loop, does the radius increase? No, you're basically just wrapping the wire exactly perfectly on itself. You assume it doesn't like get wider. You just wrap it many, many times.
So what radius can give you
It's kind of dumb. There honestly shouldn't be an n in that equation. No one uses it. Yeah. Okay, back to here. So this equation is about a solenoid and the magnetic field near a solenoid. And the equation is mu naught little n, which is capital N over length, times the current going through the wire. Okay, and again, the solenoid is a cylinder wrapped in a wire with current. Okay. Now, here's a very useful thing. If you haven't done the practice test, this appears in the solutions. I use it a couple times. And we're going to use it a lot in thermo. Whenever you're talking about changing one parameter, and you're given the initial B field, and you're told you shrink it, or you crank the current, or you change the number of turns, and you just change one thing, an extremely good strategy is to write the equation for before, or maybe I'll just leave it like this, and after. So this gives you the B field near a solenoid of length L, and after I change the length of the solenoid to a new length L prime, this equation gives me the new B field. The trick, which you're going to use a lot in your life, is you divide one equation by the other, and everything that is the same will cancel out. So I'm going to divide the B prime equation by the B equation. Okay, I'm going to divide the left-hand sides by each other, and I'm going to divide the right-hand sides by each other. But since I haven't changed n or I, pretty much everything cancels, except for the L's and L primes. Okay, dividing by 1 over L is the same as multiplying by the reciprocal of 1 over L, which is L. So I have L over L prime on the right. Again, you may be able to do this in your head, but for those of you who can't. Okay, so this tells me that B prime, the new magnetic field for the new length, is L over L prime times the original magnetic field. Okay, L, the original length, is 6 centimeters, and the new length is 3 centimeters. Okay, this number is 2. So the new B field is twice the old B field. Okay, so you get 72 millitesla from doubling your original. Okay, this strategy of dividing, writing the equation before and after, and then divide the two equations is extremely, extremely useful. We're going to use it a lot in thermodynamics where we talk about compressing a gas, so you're only changing its volume, and things like that. So I'll put this in a nice colored box. And you use this in the next problem too. So in this case, you're asked about the B field near a wire. And you're told at this point on the left, it has a strength of some constant number, B0. And you're asked, is the B field over here at point B, is it half of that, double that, a quarter that? Okay, B field near a wire is mu naught I over 2 pi r. This gives you the magnetic field a certain distance from a wire. It also works for fat wires. If I make r twice as big, B decreases by a factor of 2. Right? If I, instead of plugging in 30 millimeters here, I plug in 60 millimeters, B has gone down by a factor of 2. So it's going to be the original magnetic field divided by 2. If you wanted to do it the way we did on the last slide, where you write out the equation like post changing the distance, okay, you can again divide these two equations by each other. And the only thing that's changed is r, so every other number cancels out. So b prime over b is 1 over r prime over 1 over r, which is r over r prime. Okay, and r over r prime, r old over r new is 1/2, because r prime is twice as big. So that tells you that b prime is 1/2 of the original b. And this is the very formal way, but if the distance is double, it's very easy to look at the formula and say if I make r twice as big, b goes down by 1/2. Okay, this is a question we did in lecture, I think, yesterday. So I just want you to review it on your own. I just want to say that it's a classic question. Again, I don't know exactly what's going to be on the exam. I'll discuss with Paul. But this is a classic question, and it's a great way to test if you understand the Biot-Savart law. Okay, you'll be using the right-hand rule for it, obviously. And just another fact, again, a north pole of a magnet spits out the B field. So whichever side is spitting out the B field, that's the north pole, if you're approximating this as something sort of like a magnet. Okay, here is a doozy of a question. Yes? The last one, it would be, it's in the answer key to the thing. Left, I think. Okay, so this is a question that is about the Biot-Savart law. It's like a full-strength numerical calculation. So I'm going to give you the sketch of how you get the answer. First, let's just get the direction. Okay, we can worry about the exact magnitude later. So you're talking about the creation of a magnetic field, not the force experienced in one. So the instruction is take, for a positive charge at least, take the direction of V, cross it with R, and whatever direction that spits out, which is out of the page, that's the direction that B is in. So B is definitely out of the page. To get the magnitude of B, you have that other formula for the magnitude of the Biot-Savart law. Okay. Theta is the angle between V and R. R goes from the creator to the observation point. So you would plug in theta equals 30 degrees. Q is the electron charge, and radius is 0.03 meters. Okay, again, it's the total diagonal distance from the source to the observation point. Yeah, and again, this is a proton. That's why you're using Q equals 1.6 e minus 19. It's the charge of the object creating it that appears in the Biot-Savart law. If it was an electron, you can still use positive 1.6 e minus 19 because you have assigned the direction correctly using the right-hand rule. But you need to remember it's the opposite of the right-hand rule for B. You do V cross R and then flip your answer to get the correct direction of B. Yes? Sorry? Yeah, this should be on the equation sheet with the variables in it. Okay, two more quick ones. This one is about, this is on the homework. This is a very good question. It's about if the magnetic fields add up or cancel each other due to each of the two wires. So what direction B field does I1 create at point G? I cross R gives me into the page due to the left-hand wire. Okay, so I1 creates a B field into the page. B due to wire 1 is into the page. And I2 has I going down. R points from the wire to the observation point, and I again get into the page. So both of them create into the page magnetic fields. So the answer is they're definitely, the resultant from adding the two arrows is still into the page. If I2 were the other direction and they were perfectly the same size and distance, they would cancel each other. One would be out, one would be in, and they add up as vectors to 0. They would add up if it were reversed. Okay, this one I just want to point out for power. Remember, there are 3 equivalent equations. There's V squared R, IV. You can use any of them. You don't have to do extra work. As soon as you have V and R, you're done. And then last one, and then we'll take the poll on which day works. RC circuits, so there's a couple equations. This is more of a conceptual question. It asks you to compute the time constants, which is RC. So it's 24 microseconds here and 9 microseconds here. And it asks you which discharges faster. Okay. Remember, the time constant tau tells you like over how long, how many seconds does it take for the capacitor to discharge 60% of itself. In the case on the right, it only takes 9 microseconds for it to discharge 60%. Whereas in the case on the right, it takes a whole 24 seconds or microseconds to discharge that same amount. So the circuit on the right discharges faster. Again, because small time constant means things happen really fast. It only takes 9 microseconds to lose a lot of charge. Okay, so that's the end of the problems I wanted to do. So I just want to, like I said, take a poll really quick. Think for a second, maybe take your phones out and check what your exam schedules are. Jordan just texted me back. He said he thinks the 12th will work better for him, but if it's horrible for you guys, I'll flip it. Okay, so May 6th. Who could do May 6th? Oh, sorry, the time. It'll be like 1 to 4 p.m. or something. Like, what's up? It's horrible? Oh. All right, who could do the 6th? This is Saturday. Saturday from like, like I said, like 1 to 3 or something like that. 1 to 4, 2 o'clock maybe. Okay, and who could do the 13th? Or sorry, the 12th. That's that next Saturday. Okay, so it looks like it's pretty much a wash. I'm just going to see what Jordan can do because he'll be in town for that. I'm looking forward to this. This is going to be extreme. This is going to be pretty hype. All right, I'll see you guys on Wednesday. I'll let you know I'll have office hours, extra time on Wednesday. See you then, and enjoy the break.